Hello, good people. We did the diagram representations of gears. Now that we know how to do that, we are now moving on to the kinematic relationships. But before we do that, we first need to talk about the module of a gear. What is that? Well, the module of a gear is a parameter that tells us how big the teeth are. So the module is equals to the diameter of the gear. I think that's the pitch circle diameter over the number of teeth. So if a gear has got a larger module, if M is large, it means that D is probably large and N is small. So we have very few teeth for a large diameter. So the teeth are going to have to be bigger and wider to cover up the diameter, the full diameter of the gear. And if M is small, it means that we have a lot of teeth with a very small diameter. So if the diameter is small and there are so many teeth on that gear on that small diameter, it means that the teeth are going to be teeny weeny so that they can all fit. So that's what the module tells you. Basically tells you how big are your teeth, how wide are your teeth. Okay, yeah. So for example, I believe gear B has got, they seem to have the same module. Oh, by the way, uh, when two gears are meshing, they have to have the same module. It only makes sense. I mean, how can big monster teeth mesh with little baby teeth? The transmission won't work right. So meshing gears have got the same module. So A and B have got the same module. Now we're gonna multiply both sides by n. We get m times n is equals to the diameter. We go back to our basic math. This means that the number of teeth is directly proportional to the diameter. What does this mean? Mathematically speaking, it means that n1 over n2 is equals to d1 over d2. It means that the ratio, if things are directly proportional, their ratios are the same, taken in the same order. So diameter is directly proportional to radius, which means this is also equal to R1 over R2. Now that we've got that locked up in the bag, let's move on to our velocity ratio. So our velocity ratio is also known as the transmission ratio. We need to define it first. So gear A is the driver and gear B is the driven. Let's label them gear 1 and gear 2. Gear A has got N1 number of teeth, gear 2 has got N2 number of teeth. Gear A has got a radius R1 and gear 2 has got a radius R2. Uh, Gear A has got a torque T1 and gear 2 has got a torque T2. Uh, our gears are rotating, so they have an angular speed, not a, they have an angular speed. So this one has got an angular speed omega 1, this one has got an angular speed omega 2. We are talking about angular speeds as opposed to linear speeds because we are rotating, not going straight. Now, what is the definition of the velocity ratio? The velocity ratio is the ratio of the output speed over the input speed. What am I saying? It's the ratio of the driven over the driver, which is equals to omega 2 over omega 1. This is what you need to know. You need to know the definition of the velocity ratio. It is the definition of the gear that is the out that is at the it's the definition of the output over the input. The output is the one that is driven. That's where we get our output. And the input is where we put our input torque, the driver. So that is the definition of the velocity ratio. It's the ratio of the output speed over the input speed. And then from there, we need to find how this ratio relates to the number of teeth, to the radius, stuff like that. So to do that, we know that at this point where the gears mesh, let me change my color to that. At this point where the gears mesh, they have a common tangential velocity, too thick. There is a common tangential velocity there. Let's call it V. So V for both gears is the same at this point because it's the same point. The tangential velocity at a point is the same. And these gears happen to be meshing at that point. So both of these gears have got that speed at that point. So that means that V is equals to what's linear velocity from angular velocity? It's omega r. So omega 1 r1 is equals to omega 2 r2 because their tangential velocities at that point are the same. And then we're going to get our ratio. That means that omega 2 over omega 1, divide both sides by omega 1, is equals to, we're left with R1 over R2. And we know from here that this is directly proportional to the number of teeth. So this is also equals to N1 over N2. And God willing, if you're dealing with diameters, it's equals to D1 over D2. So there you have it. These are your your relationships. This is how you get your velocity ratio. One thing to note though is that in a external gear train like this, if gear A is going in this direction, gear B will be going in the opposite direction. So direction changes at each transmission, at each meshing point. But in an internal gear train, the one I talked to you about, that one with a big gear and a small baby gear, yeah, if gear A is going clockwise, the bigger gear also goes clockwise. There's no swap in direction. Now that we know about the velocity ratio, let's move on to the torque ratio. Same as the velocity ratio, the torque ratio is also a ratio of the output torque over the input torque, which is a ratio of the driven torque over the driver gear's torque. So torque ratio is equals to T2 over T1. Then this is where you need, now we want to relate it to the number of teeth and all that. So first and foremost, what do you expect? If a small gear, right, is transmitting its motion to a bigger gear, what do you expect? The bigger gear is going to go slower, but it's going to have more torque. So bigger gears go less fast, but they have more torque. Also, if you look at this one, gear A is way bigger than gear B. So when gear A rotates once, gear B is going to make maybe 3 rotations for that one rotation. So it's going to be going faster because it's doing more rotations in the same span of time. But then it's going to have less torque. So the torque is proportional to the number of teeth. Okay, it's proportional to the diameter. Bigger gears are going to have more torque, and smaller gears have less torque, even though they are going faster. So you have to know that you trade off your torque for speed. You trade off your speed for torque. If you want to go fast, well, you're going to have less torque. If you want more torque, you need a bigger output gear, but you're not going to go as fast. If you want to go really fast, make sure that your output gear is small, but it's not going to have that torque, that force. So torque is directly proportional to the size of the gear to the diameters. So T2 over T1 is equals to D2 over D1, which is equals to R2 over R1. We're getting this from here, which is equals to N2 N2 over N1. So there you have it. Let me also put a box around these relationships. So that is how you get your torque ratio and your velocity ratio. You don't need to cram these things, you just need to know them. Yeah. And it's pretty intuitive. For your velocity ratio, you need to consider the point that at the point where the gears are meshing, they have the same speed. Torque ratio, you need to know that the torque is, the bigger the gear, the more torque it has, and the size of the gear is basically proportional to its diameter and the number of teeth. So it's straightforward there. And then here you use that whole point of common tangential speed, and then you go on with your relationship that you got from the definition of the module. That is all for today. So now that we have these relationships under our belt, we're now going to be using them to do fun stuff, which is work out problems. Yeah, now we need problems.